Okay, thanks very much. So today I want to try and convince you all that radar data is essential really for the Artemis program. I'm part of the science team on Mini-RF. I'm going to talk about the data from our instrument, but I also want to cover the data from the DFSAR instrument on Chandrayaan-2. So radar's had a long heritage of landing site support. It's got huge implications for sort of understanding engineering constraints. So it gives us information about surface roughness. It also tells us about rock distributions, not only on the surface, but really importantly on the subsurface. Now, when we consider sort of landing architecture for the scale of putting humans on the moon, sort of the descent thrusts on that, plumes will expose a lot of rocks if they're there on the subsurface, and can also possibly inject rocks as well as during the landing. So we need to understand their distribution. It can also tell us information about radar reflectivity. Why is this important? Well, most landings involve a radar descent altimeter, and there are naturally stealthy terrains or materials on planetary surfaces which could influence that, which could obviously be very dangerous. As a result, more recently, radar's been used to part of the landing site selection for a lot of Mars missions, both the rovers and recently the InSight mission, including Arecibo data from Earth, with the example shown on this figure. So even quite coarse radar data there has been really helpful. But also very importantly as well, radar is really important for understanding science. There's a real great science application to this. You can see in that image here, the white arrows point to these buried lava flows, which are not easily identifiable by sort of images or other sort of data sets for use for mapping. And so we can really tease out a lot about the landing sites here. Okay, so basically how does radar work? In a really simple way, you transmit a signal towards the surface, and then you record the reflections that return. And from this, as I said, you can find information about the surface roughness and distribution of scatterers both in the surface and subsurface. Now, the scales of what we're sensitive to is relative to the wavelength, as is the penetration depth. So if you're able to use multiple wavelengths, and we do have data of multiple wavelengths to the moon, you can really constrain the subsurface really nicely and give us a sort of unprecedented view of the lunar regolith, which is great. But not only that, but you also can tease out other characteristics such as the porosity, density, mineralogy in some circumstances, even volatile content of the subsurface, which is of course really important. And because we're an active instrument, we can sort of peer into the permanently shadowed regions as well, and obviously not reliant on solar radiation for that. So Mini-RF, this is an instrument on board the Lunar Reconnaissance Orbiter. It's a dual frequency radar, can transmit both at 12.6 centimeters and 4.2 centimeters, at two different scales. It's a hybrid polarized instrumentation as well. That's very important because it allows us to calculate the Stokes parameters. And from that, we can deconvolve the origin of the scattering that we receive from the lunar surface and near surface and provide a whole range of different data products, such as circular polarization ratio, which I'll explain about soon. It was designed as a monostatic radar, so it transmits and receives from the spacecraft. Unfortunately, 12 years ago, the transmitter failed, but that hasn't stopped us. We now operate in a bistatic configuration. What we mean by that is we use ground-based assets, formerly Arecibo. Sadly, we've also lost that, but also Goldstone in California. We transmit and then bounce signals off the moon and receive them in orbit by LRO. This still allows us to collect these sort of beautiful radar images, as you can see here on the right, but also by varying the bistatic angle tells us even additional information about the subsurface, including opposition effects shown here in the middle, which could give us some information on the volatile content as well. So DFSAR, this is also dual frequency, but neatly it does S-band 12 centimeters, which overlaps with Mini-RF, but it also goes long wavelength to L-band or 24 centimeters. L-band, of course, is also being considered for the IMIM for Mars mission. And so from between these three wavelengths, we've got a real nice constraints between centimeters up to decicentimeters, which gives us a lot of information about the subsurface. So what about coverage? Well, here's a map on the left here of the candid landings regions, and you can see both at the S-band, which is 12 centimeters, and X-band, we've got near coverage, continuous coverage for these regions. And for areas where we have gaps, we're able to sort of fill those in using these bistatic collections. So there's a whole lot of data there from Mini-RF. And also for DFSAR, there's a huge amount of data collected of the polar regions. In fact, the mission's concentrated on the polar regions up to now, and you can see this nice mosaic here on the right. And so the real takeaway from this is that for every one of these candid zones, we do have radar data. In most cases, we have multiple wavelength radar data, so that data coverage is not a limitation to using radar to study these landing zones. It should be used. I already encourage anyone to use them. So just want to walk through some of the zones, give you an idea of some of the applications of the data. Here we have the perceives. We can see here on the left, you have the topographic data. In the middle here, we have the monostatic S-band 12-centimeter data. Now, of course, like anything else, it's the observation will influence the sort of return. And what I should say here is this is CPR, circle polarization ratio. This is basically a product which gives us information about surface roughness and near surface blocky distributions with a higher value mean it's rougher. And so due to the illumination geometry, because we illuminate ourselves, it can kind of have these sort of strange effects due to topography. And so my colleague, Caleb Fassett, who will give a talk on this in tomorrow afternoon's session, I encourage you, let's normalize this out to give you a better indication of the sort of variation in the surface roughness. And if we kind of do that stretch, we can get more details. You can kind of see these little red dots, these rough dots associated with small craters. And this will tell you that these craters are rough from a landing perspective. They can also tell you that these are younger craters, maybe great places to get sampling. And we also have DFSAR and L-band long wavelength data from this as well. This hasn't been normalized, so hence you see it brighter on one side than the other, but same process could be applied to this data. Moving on to the Faustini rim here, which is quite nice to compare the two different wavelengths. What you can see is this crater there, this sort of 2-3 kilometer crater. You can see that in the S-band, the shorter wavelength, you have a more continuous yellowy looking ejector blanket. When we look at the longer wavelength, which is also penetrating deep into the subsurface, the ejector blanket doesn't seem so continuous, but you do these sort of spots where it's much rougher, where you probably have like blocky material, and you also maybe have some melt as well. And so by comparing the two data sets, here you get a nice kind of sort of three-dimensional structure of this ejector blanket, which can help you with, once again, sort of sampling or exploring that crater. You can also see these sort of brighter, high CPR downslope to the right-hand side of this image, which could be related to sort of mass wasting, help us understand that processes. And so I just want to end here looking at sort of one application, say tectonics. You know, one of the many great discoveries from LRO has been this understanding of these small scale abate scarps, which gives an indication of thrust faults distributed all across the lunar surface, even believed to be the source of some of the seismicity we recorded during the Apollo sites. There's also indication that these are currently active from things like landslides, from albedo, like bright albedo regions on the scarps, fresh boulder fields, boulder tracks. And it, of course, also exists in the polar region. In some of the areas we're considering landing with Artemis. And the problem here, of course, is because of the sort of changing, sort of illuminated environment here that Julie was just talking about, makes it kind of tricky to sort of see maybe different surface changes at the surface with images. And so this is where radar could really help out. And if we look at sort of the Glash Rim 2, or however you want to pronounce it, region, there is one of such scarp within this landing zone, and the LOLA data covers it, shows topography here, and it's consistent with other such abate scarps seen across the surface. And so when we look at the radar data, what's really interesting is when we highlight this scarp region here with white arrows, we can see that there's a sort of this rough or blocky terrain found on the scarp sides, both at S and L band. And this is all indicates this concentration of this blocky material, which is up within centimeters to tens of centimeters in thickness within the sort of upper meter or so. And so concentration of this blocky material, the reason it hasn't broken down, may also indicate that this scarp has been recently active. And so this is one of the ways we can use it. And I'll leave it right there. Thanks very much.